Good afternoon to you and hello. Welcome to today's session of Yebo Tutor, where we'll be looking at forces, which is physical science, the physics section, your paper 1. So today you will be doing forces. The question already is showing on the screen, so we'll look at how we go about the resolving of forces, the finding of kinetic friction, and the like. So feel free to ask questions, feel free to participate. I would like to hear your view, your comments, or any contribution that you can give to us will be very much appreciated. So I'll just try and zoom into the question screen so that we go on with our first question. So with this question, this is question number 2. We did a few questions from this paper, some trial questions, which we worked out together in our previous session. So for this particular question, we have a block of mass 8 kgs placed on a rough horizontal surface. So there is important information in each part of the question, each statement there, or every phrase implied in that statement is of utmost importance. So one, we are given the mass of the block, which is 8 kg. We can see this block, it's on the table. It's on a horizontal surface. And we are told that the surface is a rough surface. So already that tells us that friction has got a role, or has got a part in this kind of scenario. Okay, so we continue the 8 kg block, which is connected to a 2 kg block by means of a light, inextensible string passing over a light frictionless pulley, starts sliding from point A as shown below. Okay, so there is also some important information there. Another block is within this setup, which is the hanging block, a 2 kg mass. So that block is acted upon by gravity. That you will never be told. It is something that as a scientist you need to conclude on your own. So we have gravity acting on that block. That is the force that drives this system. So the weight of the block pulls onto the light inextensible string. By light and inextensible, it means the weight of the string does not contribute to the forces that are in question. And it is inextensible such that the tension is uniform throughout the string. The tension is uniform throughout the string. Okay, so which means the tension due to the 2 kg block is the same tension that pulls on the 8 kg block. All right. Now, an interesting thing is also shown in the diagram. The string is at an angle of 15 degrees to the horizontal. So that means you would, in your mind, at the back of your mind, you should be thinking of components, because when you want to deal with forces, when you want to make your equations, you will need to add equations that forces that are basically in line. So for you to see the inline forces, then that means the component of the tension in the horizontal is the component that acts along the line of action of the frictional force, which in this case opposes the motion of the 8 kg block. Okay, so that's basically an analysis of the question. We should have expectations. When you see such a question, we should have expectations of what is going to transpire in our working towards the solutions. Okay, so let's see what the first part to that question says. Item 2.1 simply says state Newton's second law in words. State Newton's second law in words. How would you say it? How would you state it? How would you state Newton's second law in words? You can give us Newton's second law. State Newton's second law for us. Anyone? So you can chat with us. You can use the chat box. I'm sure when you log into your account, you can be able to also contribute or comment in the chat box from this channel. So please feel free to contact us. Feel free to communicate with us. Okay. So how do we state Newton's second law? So the question is state Newton's second law in words, and that's 2 marks. You won't afford to lose those simple 2 marks. So how would you collect the 2 marks? How would you state Newton's second law in words? So in other ways, in this case, it simply means strictly no equations. But the equation is there to guide you as to what Newton's second law is about, and you can construct that definition from Newton's second law. So in Newton's second law, we talk of a net force or an unbalanced force. So if we have an unbalanced force on acting on an object, we know that the object tends to accelerate or to move. So when it moves, if it was initially at rest, it will start moving. That means it will accelerate. If it was already moving, it might increase its velocity or its speed or decrease its speed. But that is the effect of an unbalanced force or a non-zero force acting on an object. So the acceleration is also in the direction of the force. So we can now state Newton's second law in words by saying, if a non-zero force or if a net force acts on an object, the object accelerates in the direction of the force with an acceleration which is directly proportional to the force and inversely proportional to the mass. So we'll have, in this case, I think you know, maybe to start from here, force is mass times acceleration. So if this is a net force, a non-zero force acting on an object whose mass is m, then the object accelerates with an acceleration which is in the direction of the force, same direction, and is directly proportional. So I'll use proportion there. The acceleration is directly proportional to the force and inversely proportional to mass. So that is Newton's second law, simply put. So you could paraphrase, you could say it in other words, but what is the most important is for you not to miss the issue of the directions for the acceleration and the force, the proportion between acceleration and force, and the inverse proportion between acceleration and mass. So that is a complete statement for Newton's second law. Okay, so we'll see what the second part of that question requires us to do. The second part, which is 2.2. 2.2. So for 2.1, we were defining Newton's second law. That's Newton second law. So the question strictly advised it should be in words. This is just a mathematical relationship and it will not earn you any marks, but it is good for you to know it so that you can refer to it and construct or recall Newton's law from it. So Newton's law talks about the net force or a non-zero force or an unbalanced force acting on an object of giving the object an acceleration which is in the direction of the force. So the vectors there are showing direction. And that acceleration is directly proportional to the force and inversely proportional to the mass. So that's how you would give a statement or state Newton's second law. So now part 2.2 requires us, let's see the question again for part 2.2. Draw a labeled free body diagram for the 8 kg block. Draw a labeled free body diagram for the 8 kg block. So in this case, what is required is for us to present all the forces that are acting on the 8 kg block. What are the forces acting on the 8 kg block? So we will use a simple diagram for the block. And if the block, from the center of the block is initially the weight of the block, we'll give it a symbol W. Then since the block lies on a horizontal surface, there is a force acting normal to the surface, which is a reaction force from the surface. We call that a normal force, N. Then we also have, according to the diagram, what other force is present. Let's see. We were told this is a rough horizontal surface and we have a string pulling to the right, the friction acting to the left. So we have a frictional force acting in that direction. We would want to call it FR. And we have a force to the right, or in this case, this will be a component. The actual force is 15 degrees like that. And this is the tension inside the rope. So how does the tension get to be in that direction? You know that when the 2 kg mass is under the action of gravity, it is pulled downwards, it pulls on the string, the tension in the string cascades to pull on the 8 kg block. So the tension is in that direction for that part of the 8 kg block. It is at 15 degrees to the horizontal. So maybe you can tell us what happens on the other side. So we've already, this is the free body diagram, we're done with this. So this is just a comment that I'm gonna give. We have that block, the table, then from the table, a pulley, then there is the string with the 2 kg block, like that. And that angle we're told is 15 degrees. So this is the diagram, a 2 kg block. I've just redrawn what the diagram that the question was showing. So this is an 8 kg, the 8 kg block. So we're saying the weight of the 2 kg block, let's call it what? 2g. Mass times g. So we'll call this 2g, we'll call this 8g. Then the tension in this part of the string is upwards. But the tension on the left side of this setup is in that direction. The tension is what pulls the 8 kg block. So this tension is the same. It is the same tension because we are told the string is inextensible. The string is light and inextensible. Okay, so that's how we deal with the forces in this diagram. And we can move on to the next part. What does it say? Now, when we're told that when the 8 kg block reaches point B, so we have points there, there is initial point A. I can use a different. So let's say we start at A, then that's point B. Do we only have A and B in that diagram? So C is towards the end, somewhere at the end, C. So let's say point B is close to the center and point C towards the end. That's better. Okay, so I've redrawn the diagram with points A, B, and C showing. So the diagram, the question goes on to say, when the 8 kg block reaches point B, the angle between the string and the horizontal is 15 degrees. So at point B, which is what we were just drawing, we're told that at that point, the angle is 15 degrees. So already that tells us something about that angle. The angle changes with position. If we're at A, the angle is smaller. We go to B, the angle is 15. We go to C, the angle is even greater. So that angle increases as we advance towards the pulley. The acceleration of the system at that point is 1. So we have an acceleration equal to 1.32 meters per second squared. So I'll show my my working screen in a moment. But what we want to know at the moment is, the question says, give a reason why the system is not in equilibrium. Okay, so the question for this part, why is the system not in equilibrium? Why is the system not in equilibrium? Yes, Fiscolite, we saw a few messages from your side. How are you doing? We are happy you have you joined us. But why did you retract those messages? What were you saying? We need to see what it is that you were saying from your end. Okay. So guys, we are saying the question is, why is the system not in equilibrium? So what are the conditions for equilibrium? Equilibrium would mean equilibrium. The conditions for equilibrium are F net equals to 0. If F net equals to 0, A equals to 0. A equals to 0. So there's no acceleration when the system is in equilibrium. The net forces acting on the object are also equal to 0. So this can be linear forces. Also, maybe we can say if you remember moments, the clockwise moments will be equal to the anti-clockwise moments. So for moments, basically moments are torque, so we can talk of net torque is equal to 0. The net torque is equal to 0. The moments will also be equal for clockwise and anti-clockwise. Or maybe forces to the right equal to forces to the left, forces upwards are equal to the forces that are downwards. So that is F net, the resultant net force, or the unbalanced force, is equal to 0. So this is the condition for equilibrium. Now, when the question asks why the system is not in equilibrium, it is because there is acceleration. The acceleration is not 0. So for this system, acceleration is not 0. Also for this system, there is a net force acting in the system, so it is not in equilibrium. Or we can say there is an unbalanced force, or the net force is not equal to 0. So that is why the system is accelerating. It is not in equilibrium. Then the next part, use the 2 kg mass to calculate the tension in the string. So we want tension in the string. So that part requires us to find tension. T, we called it T. So according to our diagram, where is the diagram? We can, the 2 kg mass is this one. And since we are given the acceleration of the system, this is the same acceleration, A equals to 1.32 meters per second squared downward. So the same acceleration, it is the same tension throughout the string. It is the same acceleration for the system. So the 2 kg mass accelerates at 1.32 meters per second. And as it pulls the 8 kg object, it is also accelerated at 1.32 meters per second squared, which is the same acceleration. So which means we can create an equation there by looking at the forces. We were told, we are given a clue that we should use the 2 kg mass. So which means weight, in this case, the weight of the 2 kg mass minus the tension, which is upwards, will be equal to, those are the two forces acting on the 2 kg block. So the two forces result in a net force in the vertical, net vertical force. And this means this net force is equal to the mass, which is the 2 kg times the acceleration of this system. So we have created an equation. We know W, we don't know T, but we know M and we know A. So which means T is the only unknown. So let's find out what T is. So we'll rewrite the equation. W minus T equals to M times A. So where W is the weight, which is the mass, times the gravitational acceleration minus the tension equals the same mass times the acceleration which we are given. So the mass is 2 kgs, so we'll put 2 kgs there. G is 9.8 meters per second squared minus T, which is what we need to find, equals to 2 kg times 1.32 meters per second squared. So that means if we multiply 2 by 9.8, that should give us 19.6 kg meter per second squared. Then minus T equals to, this is 2 times 1.32 will be 2.64 kgs meter per second squared. So if you take note, the kg meter per second squared is mass times acceleration, so it's a unit equivalent to the Newton. So we'll use Newtons in place of these SI units. So if we make T the subject, it means we have 19.6 newtons minus 2.64 newtons equals to T. So we take t to the right-hand side, we take 2.64 to the left-hand side. And what does that give us? What does that give us? What is t? So you can use your calculator. So that's 19.6 minus 2.64. This gives us 16.96 newtons. So the tension in this system is 16.96 newtons. Well, I hope that is clear. You guys should be able to follow this. It should be quite straightforward. Okay, so let's look at the next part. Calculate the kinetic frictional force between the 8 kg block. Calculate the kinetic frictional force between the 8 kg block and the horizontal surface. Between the 8 kg block and the horizontal surface. So that's part 2.33. 2.3.3. We want the frictional force. So how do we deal with that one? We know that our block is lying on the rough surface. Friction, we called it FR, is in that direction. The tension is pulling at 15 degrees to the horizontal. So we have tension pulling in that direction, and that direction is 15 degrees to the horizontal. Okay. And as tension pulls like that, the acceleration A is 1.2 meters, 1.32. Let me cross check. So that, yes, 1.32 meters per second squared. So that's 1.32 meters per second squared, like that. So how do we find the frictional force? Take note, the question requires us to find the kinetic frictional force. So this is our kinetic frictional force. We can make an equation again. We know that the tension component of the tension in the horizontal is known as the cos theta component if the angle between that cos theta component is the one mentioned. So the cos theta component is the one that makes or subtends the mentioned angle between the vector and itself. So in this case, this is t cos 15. So it's a cos theta component because the angle between that component and the vector is the 15 degrees that is mentioned. So if the angle is on the other side, that makes the component in the vertical. So we would have another component. Let me use another. Like if we want to deal with another component, the vertical component will be t sine 15. So the component perpendicular to the cos theta component is the sine theta component. So that's how we identify our components. Given any vector and an angle, the component between the component that is given by the vector and makes the mentioned angle with itself is the cos theta component. Then perpendicular to the cos theta component is the sine theta component, right? So the angle mentioned there is between the vector and its cos theta component. That's how we know that this is a cos theta component. It is the one that is subtending the mentioned angle. Okay, so now we know that we have t cos theta. I'll continue with this purple one. I think you can still see it. T cos 15 is pulling to the right, and minus the other force is the frictional force, and these two give the net force, which gives the acceleration. So this is equal to mass times the acceleration. Okay. So t cos 15, okay, let me just remove the vectors there. We've already assigned the signs, so which means we have the directions there. T cos 15 is to the right, FR is to the left, so they subtract, and the overall force is to the right, which is the mass times acceleration. So the direction of the acceleration is in the direction of the net force. What is T cos 15? We now have T, we said T is 16.96. So we have 16.96 newtons times cos 15 minus, we don't know what FR is, we need to find this kinetic frictional force, equals to the mass. This time the mass is 8 and the acceleration is 1.32 meters per second squared. So all these are now newtons. That means 16.96 cos 15 is 16.38 newtons minus 8 times 1.32. 8 times 1.32 is 10.56 newtons, equals to the kinetic frictional force. So that means the kinetic frictional force FR is therefore equal to 5.82 newtons. So this is the value of the kinetic frictional force. Okay. So if that is also clear, I think we are good. We can go on to look at the next part. So as the 8 kg block moves from B to C, the kinetic frictional force between the 8 kg block and the horizontal surface is not constant. Give a reason for this statement. So let's look at the diagram. As the 8 kg block moves from B to C, the kinetic frictional force between the block and the surface is not constant. Why is that? So this is the diagram we drew. Yes, this one. So as we move from A to B, we were given the acceleration. Then we found where to calculate at this point the kinetic friction, which we found to be 5.82 newtons. But as we advance towards C, we are told that the kinetic friction, which is the 5.82, is not constant. It is changing. So how do you think this kinetic friction would change? And why does it change? So already you can see that the angle between the string that pulls the 8 kg block, right, and the horizontal will not be 15 degrees throughout. So if we are further away from B, that means from A, the angle is smaller. At B, we are told it's 15, but when you get to see that angle is still increasing. So the angle is even greater. So that angle would be something like this. So that angle would be greater than 15 at that point. This will be the angle. So the angle is increasing. When that angle increases, that tells us something about the components. So we have t cos 15 becoming smaller, but t sine 15 will be increasing. So as the sine theta ratio, or when theta increases, sine theta also increases. So we are heading towards sine 90. Sine 90 is 1, sine 0 is 0. So already you can see that when you increase your theta, the vertical component increases. The effect of the increase in this vertical component is such as to reduce the normal. So the normal will reduce. Why? Let's draw the block again. We have our block. So with the block lying on the surface like that, we have a weight, the weight of the block, and the normal acting from the same point upwards. Okay, so this is case number 1. In case number 2, the same block lies on the surface and it has the same weight, but we introduce a small force. We can call this a component of T, of the tension. And when we do that, the normal changes. So in this case, N equals to W. The normal is equal to the weight. So this is normal 1. But in case number 2, the normal is still there. There is a reaction from the surface. But effectively, sorry, I need to undo that. Okay, so we have our normal is still there. But the value of the normal is W minus TC. So since W is the same, we're now removing a certain fraction of the W from the value or magnitude of the normal. So the normal, let me call it normal 2 and normal 1 are different. N1 is greater than normal for the second case. Like that. So the normal in the second case will be reduced because of the presence of that component. So the moment the component increases because of the increase in the angle as we advance towards C, then that means N will also continuously decrease. When N continuously decreases, F also decreases because the kinetic frictional force is given by mu, the coefficient of friction, times mu k, coefficient of kinetic friction times the normal. So now because the normal is constantly decreasing, the kinetic friction will not be constant. It will also be constantly decreasing. Or we can say because the angle is increasing, when the angle increases, the normal also decreases. Or because the angle is changing, the normal also changes such that the kinetic frictional force will not be constant. So I think that's how we answer to part 2.4 of this question. So besides decreasing the normal, we can also state it in terms of the component. The tension introduces an upward component which reduces the normal to the surface and hence reduces the frictional force. Now, we can look at the next part, which is our last part for the day. The horizontal surface on which the 8 kg block is moving is replaced by another horizontal surface made from a different material. Will the kinetic frictional force calculated in question 2.33 above change? Choose from yes or no and give a reason for your answer. So when the surfaces change, will this friction that we calculated here change, and you give a reason for it. So definitely, you know that friction depends on the nature of the surfaces that are in contact. So if we change the surfaces, the value of this kinetic friction will definitely change. The value of the kinetic friction will definitely change. So that's about it, guys. I hope you guys were able to follow. If you would have any questions, this is the time. You can tell us which part you want us to discuss or to explain further, and we can do that. We will happily do that. So anyone online, if you guys are gonna be seeing this from the recording, is still okay. If you would have questions, you know where to get in touch with us. If you are there on our WhatsApp platform, you are welcome to present your questions even from that platform. So from me, guys, and the Yebo Tutor team here in our studio, it has been a pleasure being with you, and we hope this video will help you with dealing with forces and questions of similar nature. Wish you the best with your studies, and take care. From me, James Jenner, it's bye-bye for now.